Hello everyone, my name is Rabbani Muhammad. I'm with my teammates Jyoti Bandari, Havar Dazi, Rahul Sai, and Sai Chaitanya. So today's problem statement is about estimating the discriminability bias, true positive rate, and the false positive rate in the three different cases. So this study uses Bayesian inference and Markov chain Monte Carlo techniques to estimate these parameters, which are the TP, FP, in three different cases. The results showed that the parameter distribution varied across the different scenarios, emphasizing the importance of considering different cases in parameter estimation and usefulness of Bayesian modeling. So the three cases are as follow. The first case consisting of 70 true positives and 50 false positives, which are observed in 100 targets and 100 noise trails. And the second case consisting of 7 true positives and the 5 false positive are observed in 10 targets and 10 noise trail. And the case 3, which is similar to the case 2, which is 10 true positives and no false positives in 10 targets and 10 noise. The further will be explained by my teammates. Over to you guys.
Discuss about the theory regarding our project first. Bias in binary classification task reflects the observer's tendency to favor one class over another regardless of the stimulus actual class membership. Discriminability or sensitivity measures the observer's capacity to distinguish between two classes by calculating the difference in means divided by the standard deviation. True positive is the number of correct positive predictions, which instances that belong to the positive class that are currently classified as positive, and false positive is the number of incorrect positive predictions, which instances that belongs to the negative class that are incorrectly classified as positive. Binomial distribution is a theoretical plausible probability distribution that describes the probability of observing a specific number of successes in a fixed number of independent trials, assuming a constant likelihood of success in each trial. Additionally, the p of x function is a mathematical tool used to calculate the cumulative distribution function CDF of the normal distribution, while the error function is a special function that can be used to calculate the probability of random variable falling within a specific range of values. We used these concepts to build a model in PyMC3 to solve the problem statement.
Now let's move forward to the code used in this project and the exploratory data analysis that we did. So this code performs a Bayesian inference to estimate three binary classification models: true positive, false positive rates, discriminability, and the bias. Each model has a different set of observed data defined in the observed data dictionary. The models are defined using the PyMC3 probabilistic programming library. As can be seen in the slide, the observed data dictionary contains the observed number of true positive, false positives, the total number of positive samples, that is target, and the total number of negative samples, that is noise, for each model. Next, the code defines a phi function which computes the cumulative distribution function of a normal distribution. Phi is a mathematical function that is used in statistics to calculate the cumulative distribution function of a normal distribution, but as it is not defined in PyMC3, so we have defined it for our model. Here ERF stands for the error function, which is a mathematical function used to measure the probability of a value falling within a certain range. So it is defined in the Tanio.tensor module of PyMC3. This function is used to model the probability of each model correctly, classifying a positive sample as positive and incorrectly classifying a negative sample as positive, that is false positive. So three PyMC3 models, model 1, model 2 and model 3, have been defined here, each with their own priors and likelihood for the observed data. The priors are specified as normal distribution for latent variables discriminability and bias, with mean 0 and standard deviation 0.5 and 2 respectively. The binomial distribution is suitable for this likelihood model in the scenario, as it models the probability of the observed data by considering the number of true positives and false positives in a fixed number of trials. So this is how we have modeled three different cases.
In this section, we will talk about our findings. For Model 1, which is 70 true positive and 50 false positive, are observed in 100 targets and 100 noise trials. Discriminability, which measures how well the model can distinguish between the two classes, the mean value of 0.464 indicates the model can moderately discriminate between the classes. The standard deviation of 0.17 suggests some variability in this measure across different samples. As for the bias, it measures the extent to which the model predicts one class more frequently than the other. The mean value of minus 0.262 suggests that the model has a slightly tendency to predict the negative class, class 0, more frequently than the positive class, class 1, with a standard deviation of 0.091. True positive rate for class 1 measures the proportion of actual positive cases the model correctly identifies. The mean value of 0.688 indicates the model correctly identifies around 69% of the positive cases, the standard deviation of 0.045. False positive rate for class 1, which measures the proportion of actual negative cases incorrectly identified as positive by the model. The mean value of 0.512 indicates the model incorrectly identifies around 51% of the actual negative cases as positive, with a standard deviation of 0.048. We can see the distributions for Model 2 and Model 3, as well as table that shows discriminability, bias, true positive, and false positive for the both model.
In conclusion, our study examined the participants' performance in a target detection task across the different experimental conditions. The results revealed that discriminability base, true positive rate, and false positive rate was influenced by both experimental conditions and stimulus characteristics. In case 1, participants had a moderate discriminability and a relatively high false positive rate, indicating some ability to distinguish targets with a high false positive rate. However, in case 2, performance improves with high discriminability, low bias, and reduced false positive rate. Finally, in case 3, participants demonstrated excellent accuracy in target discrimination with minimum false positives. The varying results highlight the importance of experimental factors in shaping performance outcome. By utilizing PyMC3, we are able to estimate parameters and gain valuable insights to the cognitive progresses underlying target detection task. Thank you.